One moment, please. Okay, so today we are going to continue our discussion on CPU performance equation. In the previous class, we started that how do I quantify the performance of a given processor, and we talked about certain equation. And so today I would also introduce two more concepts. One is Amdahl's law and the issues which are involved in die yield. Well, so let us go through the same slide which we discussed in the previous class. So here is a fundamental problem. So you have a program P written in assembly language, and you have a processor or a machine M, and you want to make an time estimate that how much time would be needed by the program P when it is run on the machine M. Okay. Because understanding of the fundamentals would be useful in order to improve the performance of the machine, right? So as we discussed earlier, so there is a very simple equation which governs the CPU time of a machine, and this involves a number of instructions in machine level language, the instruction count, and as we have already seen that execution of each instruction requires certain cycles like fetch instruction, decode instruction, execute, memory access, and so on, right? So each instruction requires certain machine cycles, and so this might differ from instruction to instruction. That's why we are talking about some average number of clock cycles per instructions, all right, or CPI. Now, CPI happens to be a very important characteristic of a machine. So we have instruction count. Now, for every instruction, I need a certain number of clock cycles, and each clock cycle requires certain duration or clock cycle time. So we have three parameters here. Very simple parameter. The instruction count is the first one, and what is the CPI? That the average number of clock cycles per instruction. This is a characteristic of the machine, the characteristic of the machine implementation, and each clock cycle has certain periodicity, clock cycle time, right? CPU time is the product of these three parameters, and if the machine runs faster, we say that the machine performance is better, right? So therefore, performance is inversely proportional to the CPU time. So now, given this simple equation that CPU time depends on IC, CPI, and CCT, obviously, in order to improve the CPU time, that means in order to improve the speed of the machine, I need to look into these three parameters. That means I need to reduce IC, I need to reduce CPI, and we try to reduce CCT as far as possible. Okay. So in the later part of the course, we'd see that how you can improve this CPI value, this IC value, and CCT value. And so today I'm going to discuss what are the factors on which this IC CPI would depend, and also this CCT would depend. Let us consider the CCT, the clock cycle time. What is clock cycle time? You know that there is a synchronizing clock, right? And the clock ticks every second, and the clock has certain frequency, and these are called system clocks. For example, if the system clock frequency is 100 megahertz, it means that the clock ticks 100 million times every second. So nowadays you have machines with several gigahertz range frequencies. So if you look into this diagram, so it shows that, so this is the clock cycle, which is a periodic train of pulses. And there are this leading edge and a trailing edge. So normally what happens in a synchronous system, the flip-flops are so designed that they change state at the transitions, like for example in the leading edges. So that means whatever update, that means the flip-flops are updated only at this time. And that is necessary so that everything works in a synchronous way in order to avoid chaos in the system. And data transfer and computation, that is being performed here, in this period. And it is updated here, right? Okay, so another thing is the frequency is inversely related to the clock cycle time. So that means if I have a 100 megahertz clock frequency here, so then the clock cycle time would be the reciprocal of this, 1 by 100 megahertz, which is this. There is so many, and it turns out to be 10 nanosecond. All right. Now my question to you is the following: that what determines this CCT? I know that if I can reduce CCT clock cycle time, my performance would improve, right? My CPU time would reduce. So why not reducing clock cycle time? I mean, whatever you want. But can you do that? That is the question. So I present before you certain numbers, and this numbers refers to certain living creatures. For example, the number 200 is related to a rabbit. 460 refers to a sparrow. 245 refers to a chicken, and 7 to 30 refer to a human being and an elephant. Could you please tell me what these numbers refer to?
Heartbeats.
Yes. So you see, there is a difference, right? There is a, so if the creature is small in size, you see. So this is some kind of general trend, not absolutely correct, but the general trend is as follows: when this creature is small, small in size, see, the heartbeat is faster. This is so many beats per minute. For human being, we know that it is around 72. Elephant is a big element. It is 30. So could you please tell me why, just from common sense, could you please tell why such a difference is observed in nature? Why such differences are observed in nature? What is the necessity of heart? It pumps blood, right? There is a periodic contraction and relaxation. So when the heart contracts, the blood pumps out and it should reach all the different parts, different body parts, right? To the extremities of the body, including the extremities of the body, right? And when the heart relaxes, the blood is pulled back to the heart, and this periodically this continues, this goes on. Okay, contraction and relaxation. So why is the difference in the heartbeat?
So there might be two things that might affect it. The first thing is the amount of energy or amount of work that each muscle of the being is doing. For example, like the bird has to flap its wings, so the heart has to pump more blood in order to provide more energy to that part. And the other thing,
but see, for elephant, it's more, right, more energy. But see, the beat is slower, right?
Yeah, but the amount or the frequency of muscles that elephant moves and a bird moves are different, right? Bird moves at a faster pace than the elephant.
Well, yes, maybe. In a biological system, there are obviously many factors. But one thing is, like if you look into this heartbeat per minute, or this is some kind of clock period, right? Because heart is nothing but some kind of, it generates a periodic, it operates with a periodic clock signal like this. Okay, so as you can see, this time period of pulsating heart, contraction and relaxation should be just large enough so that blood reaches to the extremities, in one pumping cycle. So from the distance from heart to these extremities is short here compared to here, right? So it takes a longer time to reach the blood to the extremities. So therefore you have to wait. So in a clock, in a pump cycle, you need to wait so that the heart reaches to the farthest extremity. So therefore the clock cycle time here is slower here. Are you with me? This is one of the reasons in a biological system there are many other factors. But I am giving you this analogy just to understand that. So this is the time period, as you can see. And so this should be large enough so that the blood gets enough time to reach the extremities in one clock cycle. And in the return pass, it will start moving back to the heart, towards the heart. The time period is nothing but clock cycle time, and the clock frequency, or the heartbeat, maybe this is one by reciprocal of that. So in this context, let me ask you the following question: that what determines then the clock frequency of a processor? Just look into this analogy and you should be able to give me the answer. What determines the clock frequency of a processor? Just one, and there may be many factors, but you could possibly identify one of the most important factors.
The number of clock cycles for a instruction execution.
Now we are
the size of the update time, the time
Yes.
required to update.
So if the circuit size is bigger, then the signal should take longer time to reach the flip-flops, right? Therefore, so suppose you have in a circuit you have combinational collection of, combinational cloud. That means a large network of combinational circuits, combinational elements, gate elements, and there are several state elements like flip-flops, right? And signals are reaching to the flip-flops, and the flip-flops will store the updated value when the clock make a transition from low to high, maybe at the leading edge. Okay. Now there are many signal paths reaching at the flip-flop inputs. There may be shorter paths where the signal reaches faster. There may be longer paths where the signal takes a longer time to reach, right? So this flip-flop or the clock signal must wait. Must arrive at a point when all this and all the signals have already arrived here. Otherwise, the flip-flop will store an incorrect value, isn't so? So therefore, the clock period should be large enough to accommodate the delays along the critical path in the circuit, or the longest one. But it should not be too large. Then the system slows down unnecessarily. So it cannot be too small, because if it is too small, then the slower signals that will be unable to reach any changes along these signal lines would be unable to reach to the input of the flip-flop when the flip-flop is going to store the value. Because if the flip-flop makes a transition before that, ahead of that, then this change of signal would be lost, right? So the clock period should be large enough to accommodate delays along critical paths. That means that these are the longest path in the circuit between certain points, but it should not be too large.
So the size means physical size or number of gates?
Yes, many things, a number of gates and so on, but paths from which point to which point. The paths you need to consider, these are called longest sensitizable logic path. Sensitizable means it is a path where the change of signal matters at the output. There are many paths where the signal changes, there is no change in the output. So even that path is long, it does not matter. Right? It should be a sensitizable path in the sense that any change in the signal, there should be some change in the signal along that path which would determine the output. Okay, and so you look at the longest paths, and those are called critical paths. And which paths? From primary input to primary outputs, from the output of the flip-flop to the primary output, from primary input to the inputs to the flip-flops, and from output of the flip-flop to the inputs to the flip-flop. So there are 4 classes of paths. Among all these paths, you look into the longest sensitizable path and compute the delay of that path depending on the individual delay of the gates and the interconnecting wire. And your clock signal time must be greater than this delay, isn't so? So your clock signal time, the clock cycle time must be delay of this, must be greater than this maximum delay. So therefore, the CCT depends on how you are designing the circuit, right? So for example, in a combinational circuit, if the design is based on only two level of network, like AND or NAND, then the delay is shorter because the signal has to pass through only two levels. But if it is a multi-level circuit, there are many levels of gate, then signal has to propagate, is to cross many levels, right? So in that case, the signal delay would be larger and the clock signal and CCT should be made larger, and should be adjusted accordingly. So you can see there is a limitation on the CCT. It strongly depends on the hardware circuit you build. It depends on the maximum delay encountered in that network, right? So this is one of the factors. The other factor comes from the power point of view. Just to tell you very quickly that the power consumed in a logic circuit can be expressed as follows. Is the capacitive load, because each transistor has some capacitance, because there are many junctions, so therefore it floats an equivalent capacitive load. And there is an operating voltage, maybe 1 volt or 5 volt and so on in today's processor, and there is a clock frequency, the system clock. So the power is related to this. It's a capacitive load multiplied by voltage square times frequency. So as you can see, there is also, and this is the trend, as you can see. So these are the different generations of processors, and this is the clock rate. The clock rate increases, but then it reaches some sort of saturation and falls. That's because of the fact if the frequency rises, then the power consumption also rises very fast. Even though you reduce the voltage to compensate it, but how much? Because the voltage cannot be reduced it cannot be reduced indefinitely because there are other electronic issues. For example, if I reduce voltage from 5 volt to 1 volt, there is a 5 times reduction. So this will be, there will be a factor of 25 here. But if the frequency rises by 1000, then the power consumption will increase by 40 times. So there are two limitations. There are two factors which limits the value of the clock cycle time. One is the signal delay in the hardware. Other is this power requirement. Okay. So the message I want to give it to you is the following: that you cannot reduce CCT as per your will. So there are limitations. There are many issues we need to consider which determines the value of CCT. Okay. So the CPU time is therefore IC times CPI times CCT, and as you know that we have discussed that and then memory access, execute, and write back. So for example, if it is a load instruction in MIPS, first of all, you have to fetch the instruction, bring it to the processor side, instruction decode, and on decoding, you find that it is a load instruction. That means you have to compute the address, right? Sorry, there is an error here. I'm sorry. This execute should come first, and memory should go later. Okay, so I would change it. When I draw this, I made a mistake. It should be this way: instruction fetch, instruction decode, execute, memory, and write back. These two stages should be swapped. All right. So I will change it. Okay. So these are the different stages in an instruction cycle. And when I say clock cycle or machine cycle, we'd say that, well, this is my machine cycle. The time required to execute one of the stages is called should be the machine cycle. It could be different for the different stages, but let us assume that for simplicity, the time taken to execute all these individual stages is the same. Okay, so this CCT must be large enough so that this portion can be executed in one clock cycle. All right, and since the execution of these stages depends on the hardware beneath it, the underlying hardware, which we discussed previously, and therefore CCT should be greater than or equal to critical delay, as we discussed. All right. So let us look into this fundamental equation. Once again, you have IC times CPI times CCT, performance inversely proportional to the CPU time. Let us see how can you reduce the value of instruction count. If I change my instruction set, if I do if I change the instruction set architecture, the IC might reduce, right? If the instructions become a little bit complicated, then the number of instructions would reduce, right? But if the instructions become complicated, the hardware would become more complicated. Therefore, CCT might rise, CPI might also rise. So there are trade-offs, as we can see. So reduction of instruction count needs, of course, it needs some kind of very good structure for the instruction set architecture. You can use an optimizing compiler that reduces the number of instructions and produces efficient code. Even above that, at higher level, you can choose a very good algorithm which leads to a efficient code, and also optimizing code. So these are the parameters which determine the value of which determine this instruction count. Okay. What are the parameters which define CPI? Clock cycles per instruction. Number of clock cycle per instruction. Since we are taking the average, it obviously it would depend on your entire collection of instruction set, isn't it? And later on we will discuss pipelining to speed up the system, and this pipelining essentially reduces the value of CPI. Memory hierarchy. See, the memory transaction is slow. For example, in load instructions, you are waiting for the data to be retrieved from memory. And since memory transaction is slow, and therefore the CPI would reduce. But use of memory hierarchy using faster memory levels like cache and so on. The whole objective of using memory hierarchy is to reduce the memory transaction time, which in turn would reduce the CPI value. All right. And also you can improve technologies and so on, so it will have an overall impact. Right? Clock cycle time we discussed. Of course, instruction set architecture, what kind of instructions you have. So, for example, in order to execute a floating point instruction, we need a longer time. It depends on the architecture, whether it is a single cycle, multi-cycle, or pipelining. We will discuss that later. Logic synthesis, how do we design the hardware below it? And that determines the critical delay. There is a concept called retiming. This is a part of logic synthesis also. It enables you to, once you design the circuit, then you can still reduce the delay by moving the flip-flops physically in the circuit. This is called retiming. And of course, improving technology. So that, if the transistors become faster, so then the clock cycle overall delay would reduce and so on. So this is the overall landscape of how which determine these three factors, and in turn it would determine the CPU time. All right. So here is the summary. You can look into this, that performance depends on many parameters like algorithms, which affects the instruction count, maybe CPI also, programming language, compiler, optimizing compiler, instruction set architecture, influences all three parameters. CPI is affected by memory hierarchy, use of cache and different kind of memory levels. Concept of pipelining also improves. If we implement pipelining, it will also improve CPI value. CCT is affected by logic design technology. So this is the summary, and you can see this is the overall picture. You can see that in order to improve the CPU time, so these are the things. We have so many handles, How do when we think of designing a new generations of machine, and if you are asked to improve the performance of the processor, you can see that. So these are the parameters, and you can think of that how you can improve this performance of the machine, right? So these are fundamental factors. Apart from that, there are certain methodologies used in practice that can be used to improve the CPU time, to reduce the CPU time or improve the performance. So that we discuss later. So here is the question is, the question I ask you, that how to improve the performance of a machine by enhancement of one or more components. Now in computer architecture, this terminology enhancement is used. It means that you are improving some or one or more components of the original machine. So note that when computers are designed, it goes the different companies. They say, for example, Intel, they produce different generations of machine one after another, right? So that means they improve upon the previous design, and so on. And this improvement continues, and this is called the enhancement process. Now suppose in a computer you have several components, right? One component has been improved in the next generation of machine, but the remaining components remain the same. So what would be the overall impact on the performance? That is the question. Got it? Some components have been improved in the newer version, in the new generation of machine, but the rest of the components are kept as they are. So what would be the overall impact on the performance? This is the first question. And this impact is captured by what is called Amdahl's law. And there is a second question. Suppose you add more processors. So nowadays you can see multi-core processor in one chip. There are multiple cores, like 8 cores, 16 cores, 32 cores, and so on. So if you keep on increasing the number of processors, obviously you can execute your program in parallel, and therefore the CPU time would reduce, improving the performance, right? So if you keep on adding more and more processors, how the performance would improve? So these are the two questions we want to answer. So the answer to the first question is captured in what is called the Amdahl's law. Answer to the second question is captured in what is called the Gustavson-Barsis law. So improving performance in steps. That's how the computers are designed. So you have an old machine, M old, and now we are going to produce a new generation of machine, M new, which is called an enhanced machine or an improved version of the machine. And while improving this, while designing the new machine, my objective is to improve my performance, reduce the CPU time. So what I'm going to do, that I cannot improve all the components simultaneously. There are many limitations. So let us choose a certain, so this denotes certain portion or certain components of the old machine, C old. And only this component has been improved in the new version, C new. This improvement means this C old takes execution of program in the C old takes certain time. Now it would take some lesser time. Maybe this is an adder or a multiplier. Okay, so this multiplier takes, for example, 1 minute. Now I design a new multiplier here, improving the logic. So now it takes say 50 seconds. So it is improved, right? So if a certain portion is improved, what is the impact on the overall performance? That is the question. So assume that, take an example. Suppose the C old has been improved as C new, and the speed up is 2x. That means execution time for this component spent on this component is improved by a factor of 2 here. But for the remaining component, it remains the same. So it depends on which parameter then, that how much fraction of this old is, right? If this fraction is larger, then the improvement would be significant. If the fraction is smaller, then since the remaining portion remains the same, then improvement would be less, right? So assume that, so this portion is responsible for 1/3 of the CPU time. And the 2/3 of the CPU time is unaffected in the new machine. And the 1/3 of the CPU time that is being sped up by a factor of 2. So what is the total improvement, overall improvement? That is the question. So what is the overall speed up of the M new with respect to M old? that we want to calculate. Very simple. Very simple arithmetic. Assume that in the old machine, I have a program that takes 1 second. I mean, 60 seconds, 1 minute. And this portion takes 1/3 of CPU time, right? So if I have, it takes 1 minute, and so this portion would take 1/3. That means 20 seconds is spent on that portion. Now in the new machine, this component has been improved so that its speed up is 2x. So therefore, this component would require 20 seconds in the previous machine. Now in the new version, it would take 10 seconds because there is a 2x speed up, right? The remaining time would remain the same. So therefore, so this is the old machine, this is the new machine. A job submitted to the old machine, assume that it takes 60 seconds to finish. And CB the component, for example, an adder of the old machine, which has been improved to C prime to the new machine, in the new machine. Okay, so this is the component. So what is the fraction? This is the original fraction. Since this is 60 and this is 20, so the fraction is 1/3. So this is called fraction enhanced. Only this fraction of the old machine has been enhanced in the new machine, and speed up for the enhanced version is 2x. Okay. So what is the overall speed up then? What was the CPU time old? That is 60 seconds. Now what is the CPU time new? See, 60 minus 20, that portion remains unaffected, right? And only this portion 20, that has been improved by a factor of 2. So in the new machine, it takes 50 seconds. So therefore the speed up is this. So what is the takeaway from this study? Even though some component has been improved, I mean the speed up is twice by a factor of 2, but the overall speed up is just 1.2. Because the speed up refers to only a small portion of the machine, right? So if the portion of the machine, if that portion is larger, then the speed up would have been bigger. Does it make sense to you? This is Amdahl's law. All right. This is how you can express it. What is the CPU time in the new machine? Consider the CPU time of the old machine, and this is multiplied by this one minus fraction enhanced, because this is the thing which remains unchanged. So the same CPU time remains. Only for this fraction there is the CPU time reduces, and the reduction is by this factor, right? Okay, and so therefore the overall speed up is CPU time old divided by CPU time new. And this is nothing but 1 over this one. So this is what is called Amdahl's law. You got it? Any question here? Very simple arithmetic. Apparently it looks sometimes difficult, but very simple arithmetic. So as you can see, this is law of diminishing return. It has very far-fetching consequences. Okay, so unaffected fraction will determine the limiting case. Improvement of large fraction would yield higher speed up. It means that when you try to improve the machine, make the common case faster. That means if the component is used multiple times, right, and therefore any improvement for that component would impact the speed up significantly. So here is an example. Suppose we design a new machine where the floating point instructions is improved 2 times in the new machine. But floating point instruction comprises only 10% of the overall instructions, total number of instructions. So what would be the improvement in the new machine? CPU time new, you apply Amdahl's law here. CPU time new would be CPU time old multiplied by, so 10% is only floating point. So 90% is the other instructions, and that those instructions have not been improved. So 0.9 remains the same, and only for 10%, that means 0.1, that is improved by a factor of 2. So it becomes this, and therefore the speed up becomes 1.053. All right. Now suppose instead of this floating point improvement by a factor of 2, you improve it by 100x. So if we look into this relationship, which factor would change? This factor would not change. Only this denominator would change here, right? So instead of 2 here, you would have 100 here. So even though the floating point component, has been improved by a factor of 100, see the new speed up is only this. So previously, if the floating point component has been improved by a factor of 2, then the overall speed up becomes 1.053. By improving this by a factor of 100, it becomes 1.109. See this influence, because the floating point comprises only 10%. So therefore, improving a component which is responsible for 10% operation does not have a significant effect, even though the improvement for that particular component is significant. Got it? And this is the law of diminishing return. So when computer designers, they try to improve their design, they have to keep this thing in mind. All right. Okay. The other thing is, is to use multiple processors. Okay. So let us look into this slide. So you have a single processor, you execute some program, and suppose I give you multiprocessor, you have 4 cores. Obviously, you expect, do you expect 4 times speed up? I mean, at most 4 times speed up you can expect, right? But there are many limitations. What are the limitations?
Are the instructions truly parallel? Like, can we actually execute the program? Like, can we actually fully use the 4 cores all the time?
Exactly. I mean, full parallelism may not be possible. For example, this one, I have 4 instructions here. So you can see they are dependent. So instruction 2 cannot be executed until this instruction 1 is completed, because it needs the value of x, right? So all of them cannot be executed in parallel. If all of them could be executed in parallel, then we could have expected a speed up of 4, but there are some serial components, right? So here you have similar things, I mean, some portions remain unaffected, even though you have more number of processors, but that doesn't help. Statement 1 and 2 cannot be executed in parallel. They are serial components. 1 and 3 can be executed in parallel. Similarly, 2 and 4 can be executed in parallel, and so on. So there are some serial components, some parallel component. Serial component you cannot speed up, right? Parallel components you can speed up, provided you have a parallelizing compiler. Assume that S is the time needed by a single processor on the serial parts of P, and P is the time needed by a single processor on the part of P that can be parallelized. And assume that S plus P is the total program. Assume that we normalize it to 1. Okay, so what does Amdahl's law tell you? If you use the Amdahl law, it says that it by 1 by is the fraction unaffected. Okay, 1 minus fraction enhanced, that means 1 by S, the fraction unaffected, and this is the parallelizable fraction, and that this should be divided by n, right? So by Amdahl's law, the speed up is this. So if S is 10%, for example, if the serial components is only 10%, 90% is assume that 90% of instructions are parallelizable. Even then, even if you have only 10% of serial components, then the maximum speed up is only 10x, because you can increase n. You take the limit of this expression, n tends to infinity, but that won't help. As long as S is 10%, the serial component is just small as 10%, even though the speed up is upper bounded here, more than 10x you cannot achieve. So even though you have 100 processors, you cannot expect a speed up more than 10. The Amdahl's law tells that, so this is some kind of pessimistic approach. But you can also view the whole thing from a different perspective, and that's what is called the Gustavson law. I mean, things are not that bad. Okay, so by Amdahl's law, it is limited by the serial component. So therefore, increasing the number of processors doesn't help too much. However, there is a assumption here in Amdahl's law, which we have not stated yet or thought about it. Here, the assumption is the following, that the size of the job is assumed to be constant in both cases, for the serial machine as well as for the parallel machine. However, it is clear that if I have a multi-core system, it can solve a larger job size in the same time. That factor has not been considered in Amdahl's law. And therefore, this leads to what is called the Gustavson-Barsis law. And in Gustavson-Barsis law, we look into this problem from a little bit different perspective. Let S and P represent the serial and parallel time on the N-core system. We start from the parallel system first. And then suppose if S and P are the serial and parallel time in the parallel processing system, then in the single processor, what would happen? The S portion would remain as it is. For the parallel portion, which would take P time in the N-core system, in the serial in a single core machine, it would take P times N. It would take longer time in the serial machine, right? So therefore, what is the speed up? So this is the serial component divided by the parallel component, and it simplifies to this. So therefore, the speed up here increases with N, grows up linearly, grows up with N. On the other hand, see in Amdahl's law, if N increases, the speed up is bounded by S. See the difference. All right. So there are two ways of looking into that. If you have a parallel system, then the Gustavson-Barsis law is more appropriate to see how much speed up is expected. So this is an optimistic view, because a multi-core system can solve can work out a large job in the same time, right? Because you have multiple processors. So see that the Amdahl's law is pessimistic, like in the perspective, and when you have a context of the parallel processing system. So therefore, when in case of single processor you improve some of the components, you apply Amdahl's law. But when you keep on adding more number of processors, and if you are asked to estimate the speed up or the improvement in performance, then this is a better way of looking into this. Gustavson-Barsis law. All right. Well, so this slide shows you that what are the things you need to consider for improve your performance. At the bottom level, you have these transistors where functional, even the hardware level. And then at the middle, you have this instruction set architecture. Then if you have an optimizing compiler, good algorithm, so on. And so the performance is can be improved by a multitude of factors, right? It is a very, there are many factors which are responsible for improving which determine the performance of a machine. All right. So now let me just summarize this instruction set architecture. Like RISC and CISC, you have heard about. RISC is reduced instruction set computing. So the idea is keep the instruction set small and simple so that the hardware becomes simpler. Keep instruction length, fixed instruction length. For example, MIPS instruction length, all instructions comprise 32 bits. And therefore it enables easy encoding. Load store instruction set. That means, the memory access and ALU operation, they are separated. So when you are doing ALU operation like add, multiply, and so on, you access only registers which are on the processor side. You don't have a memory access here. The memory access is separate, like load and store. And by adopting this architecture, you make sure that your instruction length remain fixed. Because otherwise, if you have to access memory here, then you should have more fields here, and that would have increased the length of the instruction. And also notice that the actual address is not specified in the instruction. It's some kind of indirect addressing, right? The actual address of the memory location is not specified here. You specify only the register here. So that means in order to specify the register, you need fewer bits. But the content of the register is the address, right? So when you, that means in instruction load, you need only 5 bits here to represent T2 and to represent T1 another 5 bits. But you don't need 32-bit address information here because address is the content. Therefore, it is sort of indirect addressing. Limited addressing mode, limited operations, instruction count would be high because you have instruction sets are small and simple. So you would have more instruction, number of instructions would become large. But the CPI is low because the instructions are simple. So number of clock cycles per instruction should be limited. So it has several advantages like hardware simple and fast, decoding simple, pipelining becomes easy, die area, chip area also becomes small because hardware is smaller and so on. And performance is optimized, focused on software and so on. So these are RISC machine. These are attributes of RISC. Typical examples are here. There are many other examples. Recent examples are RISC-V, ARM, and so on. In case of CISC, complex instruction set computer, instructions are more complex. Memory addressing is also there in the instruction. And there may be non-uniform instruction length, may be non-uniform, a different length you can see. There may be a specification of multiple operand in the same instruction. It can handle complex functionalities one instruction. So the instruction count after compilation would be low, but for each instruction you need more number of clock cycles to execute because they are complex. And therefore the pipelining becomes harder. Hardware cost would increase. Compiler design becomes more involved. Typical examples of CISC processor are the Intel series. And there are previous machines like VAX and some machines on AMD, they're also on CISC philosophy. So now we summarize here 8 great ideas which determine the performance of a machine, of a processor. One is, you see that we have already talked about Moore's law, that how the technology advances with time. And so therefore you have more and more improved technology, more and more improved chip. And use abstraction to simplify design. When you design, you need to look into the problem from a top level view so that the abstraction becomes simple. Otherwise, you won't be able to design that comprises so many billions of transistors and so on. Make the common case fast. Why? Because if you can improve the common case, that means the frequency is, the common case appears many times, right? So that means if this portion is improved, then by Amdahl's law, the overall performance would be better, right? So make the common case faster. Whichever component is responsible most of the time in the CPU, improve that component. So that will improve your performance. Because that will be more common case means that the fraction enhanced should be that is large. And therefore, by Amdahl's law, it would have a significant impact. You can use multi-core to improve the performance, and this is reflected in Gustavson Barsis law, where you have seen that the speed up increases with the number of processors. Pipelining we study later on, and that also is very important technique to improve the performance. And branch prediction we will study there, so that also help pipelining. And hierarchy of memories, we discussed a little bit that memory hierarchy enables you to make the memory transaction faster, and in effect it would reduce the CPU time. And obviously everything should be error tolerant, fault tolerant. So then we need some kind of redundancy so that in terms of hardware or in terms of software, so that the system functions, the system functionality is not, the system becomes robust. So these are 8 great ideas which are responsible for designing good machines, improved machine, and so on. So as we will proceed in the later part of the course, we will touch upon pipelining, branch prediction, memory hierarchy, one by one. All right. So now, there are some few more slides on die yield. So I would upload this slide, but I I would like to give you this as a reading assignment. This is not difficult. It says that when you produce the chips, you know, many of them may turn out to be defective. Just I would like to give you a basic concept. What happens in chip manufacturing? This is called a wafer. It's a thin slice of silicon, you know, and in circular in size, very thin. And on the wafer, several copies of the same die or chip is manufactured, you know, because it's a photolithographic process. So you have identical mask. So as you can see, these small rectangles, each of them is a chip, is a die, and they are identical dies. You know? I mean, they are all. They may all of them may be processor. Okay, so there are certain parameters are given. Each small rectangle might contain 4 to 8 codes per die and so on. This is Intel Core 7 wafer. You know. So some physical specification are given here. So this is so there are certain terminologies that let me tell you. So this is called the wafer, which comprises multiple dies, and when the die is packaged, you know, you put it in a package, you encapsulate it with input-output pins, then it is called a chip. But the silicon piece is called the die. So you have a die, chip, and wafer. This is the hierarchy. So when you manufacture this wafer, and so many of the die become defective, you know, like this, because of the manufacturing defect and so on, right? Because we are talking about so many transistors in one chip, and a manufacturing process is very complex. So what is yield? Yield determines the cost, you know. So if there is one defect, you have to throw the chip, right? There is no way you can reuse it. And also the peripheral chips, so they are incompletely fabricated. They are not full rectangles, right? Hence they are unusable. So peripheral chips are unusable, and if some defect occurs, they are unusable. Only the clean chips are usable. Okay, so the yield is nothing but the fraction of good chips that is produced, and the chip cost obviously depend on yield, right? So the economics is depend on the yield of the manufacturing process. It's a very important parameter, and yield depends on this defect distribution and so on. So the companies like Intel and so on, their objective is to improve this yield, because this yield determines the entire economics. There are certain empirical relationship that tells you that depending on if there are number of defects per unit area, okay, what would be the yield? So this is the empirical relationship. There are certain parameters alpha, which is for silicon process, alpha is of the order of 2 and 3. So this is an empirical relationship, and that gives you some expression for yield. So what happens finally? It turns out this, a very important relationship, that chip cost of the chip, considering yield and everything, you know, is 4th power of die area. The basic idea is if the area of die increases, then the number of defects would also increase, right? And that would reduce the yield, and therefore the chip cost increases. And considering all the parameters, it happens that the chip cost happens to be the die area to the power 4. So therefore they want to minimize the die area. How to minimize the die area? You have to do your logic synthesis in such a way so that it becomes very optimized. And as we minimize the die area, those power and thermal issues will also crop in. They will also arise. So therefore, there are many factors which are needed to be traded off. All right. So please go through these slides. Some problems are also worked out here. Not difficult. I mean, it follows straight away from the empirical relationship and so on. So I leave it to you as a reading assignment. Okay. So in conclusion, we notice that the execution time is the best performance measure. Instruction set architecture is the fundamental thing which lies at the hardware-software interface we need to consider, and power is the limiting factor. All right, so I would upload this slide maybe by today and so on, and next class would be taken care of by Professor RSC. He would introduce MIPS assembly language, and there is an announcement that on 6th September we conduct a test during the class hour. I mean, we start from during the class hour from 12 noon and continue up to 2 p.m. And coverage will be whatever you've covered so far, and RSE will cover MIPS assembly language material covered until this. All right. I think we are out of time today and should take leave now. Any question? All right. If there are no questions, then maybe I take a leave now. Thank you.